Hey guys, so today we're going to go ahead and take a look at work and power. All right, let's jump right in. So, essential question number one, what is work? We need to go ahead and define this term in a scientific way so that we can all be using the same concept. Number two, what is power? Again, like work, we need to get a definition here, and we don't want to leave this to the ambiguity of what our general parlance is and outside of science. Okay. Number three, why isn't work always done when a force is applied? So, we've talked about briefly the relationship between work and force. So, today we're going to look at it in more detail and talk about why it doesn't always work work out that way when we go ahead and start looking at forces being applied and they don't necessarily do work. Is there such a thing as negative work? What about negative power? So we'll look at these two terms of work and power and then talk about whether or not it's possible to do negative work or have negative power. And then lastly, we'll try and relate this to your energy bill. So, how does work relate to your energy bill? All right. So, what does it mean to do work? The term work has a very specific meaning when we start looking to science. Work is only done if a force moves an object. When you push, lift, or throw an object, you're doing work. Your force is acting on the object and causing it to move a certain distance. So, work is a force acting across a distance. So, if we think about this in terms of a mathematical relationship, okay, force times distance is going to equal work. Okay, and we think about the units here. So, force is in newtons, distance is in meters. And so we have a Newton meter. If you remember from before, this is a joule. So we're going to be using the same unit we talked about when we were doing energy. Okay? All right. So not every time a force is applied is there going to be work done. A force can be exerted on an object without work being done on the object. So let us think about this idea of pushing the wall. We talked about this earlier on in the term, but if I go ahead and push on the wall, I'm definitely applying force. But the force it's pushing back with on me is enough that it's not causing movement of the wall. So is work being done? Well, in this particular sense, no. For the work to be done, the force must be applied in the same direction as the movement of the object. So when I pick up a bag of groceries, I'm doing work. But if I walk while carrying the bag of groceries, I'm not doing work. Okay. The vertical movement of the groceries and me applying that vertical force is doing work because it's force across that distance. But as I'm walking forward, I'm applying that force upward. My forward walk is in a different direction. So I'm not actually doing work in this particular example. Okay. So that's the big thing you have to realize is that in order for work to be done, your force has to be creating movement in the same direction. All right. So let's take a look at the equation for work once again. The amount of work done in moving an object is equal to the force that is applied times the distance through which that force is exerted. Okay. So work equals force times distance. And again, as I showed you before, force is measured in newtons, distance is measured in meters. A Newton meter is better known as a joule. And so the same unit that we talked about for energy is going to apply here when we go ahead and measure work, which should make some sense because energy is the ability to do work. Now, this is one thing that I've been asked a couple of times by different people over the years. Is it possible to have negative work? And the simple answer is yes. Because when we start talking about frame of reference and what we identify as the positive or negative direction, you can do negative work. You're applying a force, and when we go ahead and see our force is applied opposite to the direction, okay? So if F and D parallel point in the same direction, the work done is positive. If F and D parallel point in opposite directions, the work is negative. So we can take a look at this vector here. And when we go ahead and do so, you see that force can be broken into two component vectors, and that part of that force is being applied in the same direction as the motion. So we can go ahead and have this component here, which is not in the direction of motion, but we also have this component here, which is, and this one would be considered positive work because it's applied in same direction as when we go ahead and look at the distance. Okay, so when we go ahead and start looking at these, same direction, therefore it's positive. We're assuming this is a positive direction and that a negative direction would be going in the opposite direction. Okay. In the other example here, we have this force vector, and this can be broken into component vectors as well. Now, this vertical one is not doing work, no work, because it's not in the direction of motion. But if we go ahead and assign this is the positive direction and this is the negative direction from this point when we're looking at the distance traveled, in this particular instance, we have a force that's going in the same plane of motion. But in this case, it's going in the opposite direction. So this is what we would call negative work. Okay. It's still impacting the direction of motion, but it is not in the same direction as motion. So therefore, because of our positive negative terminology with respect to frame of reference, we can identify as yes, this is doing work, but it's doing work in the opposite direction of the motion. So this is what we would identify as negative work. All right. Okay. So here's that same thing again. You can see there's the component vector of the force that is applied in the same direction as motion, positive. And in this case, we're doing kind of the same. It's in the same plane as the direction, but there's the component vector from the force. That's opposite the direction of the actual distance traveled. Therefore, we're doing negative work. Remember that energy is the capability of doing work. This is a scalar measurement. It's something that can be applied, but work and energy are going to have the same unit, which is that joule. And if we want to go ahead and break this down into tiny little pieces, remember that a joule is equal to a Newton meter. And a Newton is a kilogram meter per second squared. But we've got another meter here. So kilogram meter squared per second squared if we're going to break this down in terms of the base units that we try to look at. Okay. So there are your base units. That's what a joule represents. Okay, so that's the basic understanding of what we wanted to go ahead and cover in terms of energy. Now we want to go ahead and move on and take a look at power, which is closely related to work. So like work, power has a very specific meaning in science. Like speed, velocity, acceleration, power tells you how fast something is occurring. But in this case, we're looking at how quickly work is being performed. So our definition here is that power is the rate at which work is done or the amount of work per unit time. Now you remember we just said that when we go ahead and take a look at the units, that work is the same as energy, joules, and that when we go ahead and do joules per time, remember our base unit that we typically use here is a joules per second. And this is going to be what we call a watt. Okay, so the unit we're going to use to measure power is watts, and this is a joule per second. Work per time. Okay, so let's go ahead and take a look at that equation. There it is, calculated by dividing work by time. But if we go ahead and take a look at this, we also have a definition for what work is. Work is force times distance. And so if we take a look at power equals force times distance over time, we have another variable that we can use here that represents distance per time. Distance per time, remember, is a velocity. And so since we can write power equals force times distance over time, we can also recognize that power is equal to force times velocity. So all of these can be used when we go ahead and start talking about power. So one thing I want to point out here is that if we're going to go ahead and talk about it this way, we can look at the units here as well. Remember, force is still in newtons, but instead of Newton meter, velocity is meters per second. So we have Newton meter per second, which is what a watt is. Okay, so watt is equal to a joule per second. Joules, remember, are equal to Newton meters. So this is equal to a Newton meter per second. And a Newton, remember, is going to be a kilogram meter per second squared. So this is going to end up being a kilogram meters squared per seconds cubed in terms of our base units when we go ahead and take a look at a watt. Okay. All right. So that's what we need to make sure we understand, that this is how we go ahead and work. A joule per second is a watt. Now, like looking at work and the possibility of doing what we would consider negative work, we can go ahead and take a look at power. And power can also be positive or negative depending on whether the force and velocity point in the same direction. Okay, if they do point in the same direction, so let's say we're dealing with um, a velocity that's going to go in this direction, and we have a force that's going to go in the same direction. This would go ahead and be positive power. If we go ahead and have a force applied in this direction and a velocity being applied in the opposite direction, we would end up with what we call negative power. Okay. All right. So let's look at some quick examples and then let's do some practice equations. So let's go ahead and apply the work equation to determine the amount of work done by the applied force in each of these three situations described below. Let's start with diagram A. Now in diagram A, we are looking at a 100 Newton force applied to move a 15 kilogram object a horizontal distance of 5 meters at a constant speed. Okay. Now, if we remember, when we calculate work, what's work equal to again? Okay. Work is equal to force times distance. And we have our force listed right here. Now we need to find the distance. Oh, we've got 5 meters right here. So work is equal to 100 newtons times 5 meters. There's your Newton meter, which is going to be a joule. So in this case, work is equal to 500 joules. Let's try B. Okay. Now this one's a little trickier because again, your force is not directly in line, so we can't use all of it. We're going to have to use our SOHCAHTOA in this particular case. We want to find out how much is in the direction of movement. We are again going to go ahead and look at an object moving at a constant speed for a horizontal distance of 5 meters, but we cannot use the full 100 newtons. So if we think about using SOHCAHTOA, we have the hypotenuse, so we're not going to use tangent. And we're looking at the adjacent, not the opposite portion. So adjacent is going to be our cosine. So we're going to use cosine of 30 degrees is equal to adjacent, we'll call that x that we've labeled here, over hypotenuse, which is 100 newtons. If you go ahead and do the math on that, cosine of 30 is going to be 0.866. A couple more decimals, and remember to keep your calculator in degrees for this. And then we're going to go ahead and times that by that 100 newtons. And so that's going to go ahead and leave us with about 86.6 newtons that we're actually going to apply. X equals 86.6 newtons. Well, now we've got a force and a distance. So again, we're going to use our work equals force times distance equation. So work equals 86.6 newtons times 5 meters. And that's going to give us work equal to 400. Let's go ahead and fix that. That's not a 4. Equal to 433 joules. Okay. And now let's go ahead and do diagram C. Now an upward force is applied to lift a 15 kilogram object to a height of 5 meters. Okay. So in this case, we need to go ahead and figure out our force. Okay. What is our force being applied? So when we go ahead and take a look at this, the one thing we can think about is that this force have to be more than what we took a look at in terms of the gravity or the weight when we go ahead and take a look at this. So the first two are easier examples. We can go ahead and say 500 joules, 433 joules. And I'll go ahead and clear this so we have some room to work. All right. Now, let's remind ourselves of those answers. We had 500 joules. We had 433 joules. Okay. When we go ahead and take a look at this, we need to go ahead and take a look at using the gravity equation. So we need to find a force, as we mentioned. And when we go ahead and do this, we're going to use F of gravity, which is weight. And that's going to be equal to, now this is getting confusing, W for weight versus W for work. F of G, let's go ahead and just use that, is going to be equal to 9.8 meters per second squared. And we'll go ahead and times that by the mass, which is 15 kilograms. Okay. When we go ahead and do that, we get an F of G that's going to be equal to 147 newtons. Then we can go ahead and do force times distance. So work equals force times distance. Work is equal to 147 newtons times the distance, which we said again is 5 meters. And we end up getting work is equal to 735 joules. Okay, there's your Newton meter. So hopefully you're getting an idea of how to go ahead and use this. We can only use, remember, what is actually in the same direction or opposite direction of the actual motion. Anything that is perpendicular, or any component that is perpendicular is not actually doing work. So keep that in mind as we go ahead and do this. All right, so we've done some examples now of how to calculate work. Let's go ahead and do some of how to calculate power. Okay, let's clear this out. All right, an escalator is used to move 20 passengers every minute from the first floor of a department store to the second. The second floor is located 5.2 meters above the first floor, and the average passenger's mass is 54.9 kilograms. All right. Determine the power requirement of the escalator in order to move this number of passengers in this amount of time. So what we're looking at here is time of every minute. So we're going to try and use that in seconds so that we can use our standard unit of a watt. So 1 minute is 60 seconds. And it's moving to a distance here of 5.2 meters with an average mass of 54.9 kilograms. So we're looking at 20 passengers. So this is the one kind of tricky part of this question here is let's go ahead and solve the amount of work per person. And then we can go ahead and times that by the 20 to get the total amount of work done for this particular scenario. Okay, so remember, in order to get work, we need to go ahead and have a force across a distance. And we are not given a force here, but we are given the mass of the individuals, the average mass. So let's go ahead and find their weight. So let's go ahead and do F of G is equal to 54.9 kilograms. That's going to be times the acceleration of gravity. And so 54.9 times 9.8, and that's going to give us 538.02 newtons. All right. So that's the force required for one person, but we have to do that person over 5.2 meters. So when we do work, and this is for one person, work 1P, we're going to go ahead and do 538.02 newtons times 5.20 meters. That's a Newton meter, which will give us a joule. So we times that by 5.2. That gives us an answer of 2,798 joules. And by that, remember, that's just for one person. One person. So then we need to go ahead and apply that to all 20 people. So we can simply take that and times that by 20. Okay. Which is going to go ahead and give us the amount of work done by this escalator, 55,954 joules. Okay. All right, so that's a good practice problem. When we go ahead and look at that, let's double check our work really quickly. 2,798 joules looks good. And for the entire minute, 55,954 joules. All right, then it says to go ahead and calculate the power requirement. So let's go ahead and do power. So we have the work done, and we double checked it, so we know our work is correct. So this is work, which should make sense because it's in joules. And if we're going to do power, power equals work per time. And so we're going to go ahead and set this up as equal to 55,954 joules. And we did that over a period of 60 seconds. Okay. So we can go ahead and divide this amount by our 60 seconds. And we get a power equal to 932.6 watts. Okay. So let's see how we did there. Where's that? And our work, 933 watts. There you go. Okay. All right. So we're getting a pretty good idea of how to do these calculations at this point in time, I hope. And so we'll go ahead and give you a chance to go ahead and try some on your own and then give you some answers. But before we go ahead and do that, I wanted to go ahead and talk a little bit about your electric bill. I don't know how much you guys look at your family's electric bill, but your household's monthly electric bill is typically expressed in what are known as kilowatt hours. What is a kilowatt hour? Well, we've just introduced you to this idea of a watt, right? A watt is an ability to do work over time. So 1 watt is going to be 1 joule per second. Now, a kilowatt hour is going to be 1,000. If we take a look at this units, okay, kilo, remember, means thousand. So this is 1,000 watts per hour. We need to compare this kind of to our units if we want to go ahead and think about that. And when we go ahead and start taking a look at this, we can use conversion factors to go ahead and start getting this into how many joules of energy this is. So let's go ahead and take a look at this. A kilowatt per hour. So let's start changing the kilowatt. Kilowatt is 1,000 watts. Okay, kilowatts cancel. 1 hour is 60 minutes. Hours cancel. 1 minute is 60 seconds. Minutes cancel, which gives us a unit of 1,000 watts per 3,600 seconds. We can do a little bit of unit canceling, zero canceling here. 10 watts per 36 seconds. Equal to 0.28, let's say. Let's do the round. It's 7 repeating watts per second. So how does this relate to when we go ahead and start talking about how many joules we end up with? Well, if watts is per unit time, right? And we go ahead and take a look at this, we end up with a number that ends up leading us to 3.6 times 10 to the 6 joules. That's a lot of energy. So you're not paying a whole lot when you go ahead and get the electricity that you use. You use a lot of energy to make up that 1 kilowatt hour. Okay, so let's kind of keep that in mind as we go ahead and move forward. And let's go ahead and try a practice problem. All right, so I'll read it to you, and then we'll go ahead and pause the video, and then you go ahead and try and work it out, and we'll go ahead and check our answers. Arizona State University football coach Bruce Snyder banished 242-pound Terry Battle. That's already converted to newtons for you, 1,078 newtons. And 205-pound Jake the Snake Plummer, 913 newtons, to the Sun Devil Stadium steps for some corrective therapy following a poor practice. The 50 stadium steps require a vertical rise of 15 meters. Battle completed 8 trips up the stairs in 195 seconds, and Plummer completed 12 trips in 270 seconds. Which athlete performed more work, and which athlete had the higher average power output? Ignore the return trips down the steps and any horizontal displacement. Just assume going up and don't worry about coming down. Don't worry about the forward motion because in terms of work, it's complicated to do 2 directions. Okay, so go ahead and give that a run. Pause the video here, try and work it out, and then I'll go ahead and give you my answers and we'll see where we're at. Okay, pause the video here. Welcome back. How'd you guys do? Okay, well, let's go ahead and take a look at individual work and power by person. So let's go ahead and start out with Battle. Battle is going to be looking at a work and power number that's going to go ahead and be somewhere around 129,360 joules, which gives us a power of 663 watts. Okay, and when we go ahead and take a look at Plummer, Plummer did 164,340 joules with a power of 609 watts. So when we take a look at the amount of work done, Jake the Snake Plummer did more work, but Battle actually had more average power in terms of his output. So Plummer, greater work, watts is going to be higher for Battle. Okay. All right, guys, I hope you got something out of this. Have a great day. Take care of yourself. Stay healthy, stay safe, and we'll talk to you soon. Take care of yourselves. Bye.